Welcome to Oddly Real. I'm Nem Stefanovic. The idea of flying through the air has always fascinated humanity. Yet, flying through the air has only been possible in the last 250 years or so with the invention of the hot air balloon. The invention of the airplane, which has made air travel practical, has only been around for a little over a century. It seems extraordinary that a body that weighs as much as a human being and even a whole passenger airliner can somehow levitate itself through a substance as light as air. How is this possible? There are many different methods to achieve flight. A hot air balloon is able to fly because it can be made to be lighter than the volume of air that it displaces. Alternatively, a propeller-based aircraft generates a thrust to push itself forward while relying on its wings to generate lift. More advanced aircraft, like jet planes, also use wings for lift, but use compression and expulsion of gas for thrust instead of a propeller. In this episode, we will explore these three types of flight systems to understand how they work. Additionally, we'll show some practical examples of the physics and engineering behind their designs. One of the easiest ways to get off the ground is by the use of a balloon. In much the same way that a boat floats on water, a hot air balloon or a gas-filled zeppelin relies on buoyancy to keep it in the air. Air is mostly made up of nitrogen and oxygen molecules, along with a small percentage of other trace substances. Air is a gas, but it is also considered a fluid, since its molecules move around freely and it doesn't have a rigid shape or structure. Amazingly, the basic principle of buoyancy has been known for thousands of years. Buoyancy produces an upward force or lifting force on an object. For example, imagine a pool of water that is filled right up to the height of its container walls. Water has weight. 1 liter of water weighs 1 kilogram. If a human being dips their whole body into this pool, the presence of their body will displace some of the water in the pool, causing it to spill out. The volume of water that spills out of the pool is equal to the volume of the human body. The weight of that water is equal to the buoyancy force on the human body within the pool. If the body weighs less than the water it displaces, it will float. The same principle applies to a balloon that displaces a volume of air. The total force of buoyancy pushing the balloon up is equal to the weight of the displaced air. The balloon will float if there is a net positive difference between the weight of the displaced air and the weight of the balloon. The weight of the balloon here would be the materials that make the balloon, as well as the weight of the passengers and the cargo of the balloon. But how can we measure the weight of a volume of air? This can be calculated if we know the air density. If we know the air density, we can find the weight of air for a given volume V with the equation that the weight of air, W air, is equal to the density, rho, times the volume, V, times the gravitational acceleration constant, G, on Earth's surface, which is 9.81 meters per second squared. Air density is usually readily available information which you can reference for a given temperature and pressure. However, it's also possible to calculate the air density using the ideal gas law using a temperature and pressure value as well. Let's determine the lifting capacity of a balloon of our own making. For example, consider a balloon that has a radius of 1 meter. The volume of a 1 meter balloon can be computed by looking up the volume formula for a sphere, which is the volume V equals 4/3 times pi times the radius cubed. When we plug in the radius r equal to 1 meter, we get the volume V equals approximately 4.2 cubic meters. Let's assume we're close to the Earth's surface at sea level and at a temperature of 15 degrees Celsius. We can look up the air density here as 1.225 kilograms per cubic meter. If we plug this value into our equation for the weight of air, we get that the weight of air, W air, is equal to 1.225 times 4.2 times 9.81, which is equal to 50.47 newtons of force, which can lift 5.15 kilograms or 11.3 pounds. Keep in mind, that's the buoyancy force. The actual net lifting force that the balloon experiences is the difference between the buoyancy force and the total weight of the balloon, its contents, and its payload. For example, let's fill the balloon with helium gas, which is lighter than air. Helium has a density 7 times lighter than air. The weight of helium for the volume of the balloon is 7 newtons, meaning it weighs about 0.7 kilograms or 1.6 pounds. Thus, if we take the mass that can support our buoyancy force being 11.3 pounds and we subtract 1.6 pounds of helium, that leaves approximately 9.7 pounds for the rest of the balloon materials and any additional payload it is expected to carry. Interestingly, we don't need to fill a balloon with a substance like helium to get it to float. It also floats using hot air to create a hot air balloon. When air is heated, its molecules acquire more kinetic energy, meaning they twist, vibrate, and travel at faster speeds. This also means that the molecules will naturally tend to space themselves out further, meaning that the air density decreases. This lower air density for hot air means that the displaced balloon volume will be lighter than the ambient air. The use of buoyancy to generate lift is based on creating machines that are ultimately lighter than the air that they displace. However, modern aircraft are much heavier than air, so how is it that they are able to fly? Airplanes generate lift using wings or airfoils. Wings produce lift by generating an air pressure difference between the top and bottom sides of the wing. Lower pressure on the top of the wing versus higher pressure below produces a net force pointing upward, keeping the plane aloft. When air travels around an airfoil, the air streams are forced to move around the body since the airfoil is obstructing the path of the airstream. The air streams diverge at the front tip of the wing, some going up and over the wing while others travel beneath the wing. In either situation, there is a conservation of mass of the airflow. There's no additional air being created or destroyed, it merely travels across the wing. The amount of air mass traveling across the wing per unit of time while the plane is in steady flight is constant. The mass that travels over the top of the airfoil tends to bunch up while it navigates around the body. This bunching up means there is less space or area for the mass to flow through. Since the flow of mass around the wing is constant, that means the only way that the mass can continue to flow at the same rate through a smaller area is by speeding up. This phenomenon is similar to what happens when we plug the end of a water hose with a finger. The water will all of a sudden start to shoot out of the hose at a much faster rate. There's a link between the velocity of the air mass and the pressure it experiences. This relationship is captured in a formula called Bernoulli's equation. It shows that the pressure plus 1/2 of the air density times the square of the air velocity is constant. Notice that if the velocity of the air goes up, like when the air passes over the top of the airfoil, that means the air pressure must go down to satisfy the equation. So to summarize, air is forced to move around the airfoil, which is obstructing the path of the airflow. The air stream bunches up as it moves over the top of the wing, which reduces the area that the air can flow through. Due to the conservation of mass, the air is forced to speed up to maintain a constant airflow. Then, by Bernoulli's equation, we see that the increase in air velocity means that there is also a decrease in pressure. The net difference between the air pressure above the wing and the air pressure below the wing results in a lifting force. We can conduct a simple experiment to demonstrate a mass flow over a curved surface and Bernoulli's principle. Take running tap water and a spoon. Here, the spoon acts like an airfoil and the water mimics airflow. Hold the spoon by the tip of its handle so that it's dangling below your fingers. Now gently bring the spoon into the flowing water stream. Notice that the spoon will experience a force that attracts it towards the water flow. The spoon experiences lift within the water stream. Additionally, notice that the air that runs over a wing takes a curved path. In order for that airflow to curve like that, there needs to be an applied force. This force comes from a higher pressure on the outside of the curved airstream toward the lower pressure on the inside of the airstream. In fact, as you move from a distance far away from the airfoil toward the surface of the airfoil, the pressure steadily decreases. The stronger the curvature of the airflow, the lower the pressure at the airfoil's surface. The shape of the airfoil influences this airflow curvature, which also influences the produced lift. Thus, the shape of the wing can be designed to modify the lift. The propeller of an airplane is what provides the necessary thrust to move the airplane forward. The blades of the propeller are actually rotating wings. This series of airfoils generates a net force or thrust in the direction of flight. Each propeller blade is twisted since the different radial sections of the blade are rotating at different speeds. The inner rotation of the blade is slower than the outer tip of the blade. The twisting of the blades accounts for these different spin rates along the distance of the blade to ensure that all parts of the blade are contributing together to the overall thrust. Finally, there are performance limits to propeller-based flight technology. Propeller airplanes are not able to fly faster than about 500 miles per hour. At higher speeds, the propellers encounter high drag, which results in larger power requirements for the engine. Jet engines produce thrust using a fundamentally different approach than propellers. The jet engine converts energy from fuel into an internal high pressure relative to the outside pressure. This pressure difference provides a net force or thrust to drive the aircraft forward. A simplified expression for this thrust is given as the thrust T is equal to the airflow mass, m air, flowing through the engine times the exit velocity, v exit. Thus, there are two ways to increase the thrust. One is to increase the mass of air flowing through the engine. The other is to increase the size of the exit velocity of the flow. A turbojet engine works by making the exit velocity extremely large. However, on its own, this is actually a very inefficient process. The exhaust of the engine produces a lot of kinetic energy that is ultimately released as wasted heat into the atmosphere. Thus, alternative designs have been created to make jet engines more efficient. A turboprop engine is a kind of hybrid engine that combines a jet with a propeller. The propeller produces most of the thrust. About 85% of the kinetic energy from the jet exhaust is extracted through a turbine to help drive the propeller. The remaining 15% of the jet exhaust directly produces thrust. This type of design is found on smaller commuter aircraft. The most popular jet engine technology on commercial flights today is the turbofan. A turbofan produces significant thrust from the exit velocity of the exhaust. It has a fan at the front and an inlet housing called a nacelle. The fan accelerates the airflow within the engine and routes the air through two paths. A large air mass is directed around the engine core through a bypass directly out of the engine at a relatively low exit velocity. The rest of the air mass travels through the engine core. The engine core consists of compressors and a combustion chamber. The compressed air is mixed with fuel and ignited to produce very high energies in the flow. This exhaust is routed through turbines to extract the energy to run the fan and the compressors. The remaining exhaust is then routed through the nozzle where it is accelerated to a high exit velocity. I hope you enjoyed this episode, and remember, oddly real, really interesting.